Hello everybody and welcome to this week's video. We are finally free of the never-ending cycle of magnetohydrodynamics, and I thought it would be fun to swing in a completely opposite direction and still remain in physics, so kind of bordering on the edge of, and look into some categorical quantum mechanics, which is really cool. Um, so basically, categorical. I mean, I got my notes from an Oxford set of notes textbook thing. Um, Now, categorical quantum mechanics is like a fusion of maths and physics. Also, I thought until I noticed that these notes had not been published by the maths or the physics department, but instead they had been published by the Department of Computer Science. So that was interesting. I guess it kind of makes sense though. The sort of main thing, from what I've gathered, that categorical QM is trying to solve is quantum teleportation, which in standard QM is kind of a pain. You end up having to do a bajillion tensor products and things, and um, today I'm going to show proofs of the lemmas, or well, two of the lemmas of category theory. You can actually just, well, the teleportation protocol gets condensed fairly massively, and it becomes much more, not trivial, but it's nicer to do. Oh, why has that happened? Full page view. No, there. Wonderful. So we'll begin. And I'm imagining not many people know too much about this, so I'll sort of try and explain as best I can. Um, so the entirety of this rests on this foundation of cups and caps. Basically, as opposed to FDQM, we're working in a finite dimensional Hilbert space. We can define a basis vector I here for some d-dimensional space H. So we have our basis vector I probably should write it just like this. For H, which is written like that because it's mathcal. And in a d-dimensional space, for a qubit, d is equal to 2. So that's mainly what we're going to be dealing with for today. But we should probably begin. So let's look at cups first. So a cup is a morphism from a scalar field C to a composite system H. I'm not sure how I would say tensor product H, the tensor product of H on H, which is the preparation of a maximally entangled Bell state. So we can define this state as eta. That's not very good. There we go. Being 1 over root d times this great big, that's not a very good sum. This big sum from d minus 1, sorry, from I equals 0 to d minus 1 of I crossed with I. It's not a cross, it's a tensor product of our basis vector I with itself. So this is our cup. And then we also aim to define the cap. So our category, what's the full? It's a symmetric monoidal dagger category, right? And what this has basically, the meaning of, or the importance of that is because it has this dagger functor conjugate transpose, the adjoint of the cup is cap. That's the name that it's given, and it is simply the bra of eta, which in physicsy language represents a projection onto a maximally entangled state, rather than a Bell state. Sorry, what am I on about? Is the projection onto the maximally entangled state rather than the preparation of the maximally entangled state. So this is actually just the transpose of the cup. I should make that a bit more clear. Or 1 over root d of the sum from I equals 0 to d minus 1 of j tensor product j. And this is our cap. So let's go into a proof, and hopefully things will start to clear up as we go through. So our first lemma 1 states that m product I cup is equal to I m transpose cup. Nice. This is our initial lemma. What is this saying? Well, if we have a linear operator m, so here we have m, which maps from h to h, sliding it across our cup, which is our preparation of the maximally entangled Bell state, transposes it. Also, so in other words, you could say that it's simply proving that an operator acting on one half of the Bell state is identical to the transpose of the operator acting on the other half. You might be able to see how this gets us to this definition of the cap. Anyway, let's begin. I'm not sure how formally I'm going to do this proof. I think it's fairly formal. But I'm not going to write proof and do all that stuff. I'm just going to write it and speak it out. So we'll let m be expanded in our basis, which is going to be over AB. So m is sum over AB of m AB ket A bra B. And what we want to do is apply our m cross I to our cup. So let's expand that using our expression of m from above. I should probably made that a bit more capital-y. So m tensor crossed with I cup is equal to, how much space will I have? We'll see. So we can then input our expanded form of m from over here, m a b a b tensor cross with I, and then our 1 over root d from up here, 1 over root d sum from I equals 0 to d minus 1 of I tensor crossed with bra I. Now expanding, or rather mathsing this, it does simplify down a fair amount. In fact, I don't even need to write that because we haven't formalized a dimension here, so I'm just going to write this over I. We can pull all three of these things into the same sum, which is really nice. So we get that this is 1 over root d times the sum over a b I of M AB, and then things in brackets. Yeah, okay. I think. Oh god, I'm already struggling, and we're like 10 minutes in. B I. Yeah, that seems right. Tensor crossed with I. Yeah. Yeah, cool. Because that, yeah. Okay. This is beneficial. Now we can evaluate this inner product, and it comes out to be our Kronecker delta on top of BI, which forces B to be equal to I in this circumstance, and that simplifies things down even further. 1 over root D over AI MAI A tensor crossed with, oh no, that should be cat I. Nice. Now we should do the right hand side, which is very much the same thing but the other way around, and a bit topsy-turvy, but it's alright. So we have the I tensor crossed with M transpose eta, or rather cup, is equal to this but the other way around, and we're going to choose a basis with dummy variables C and D here, because it's irrelevant which ones we choose, and I want it to be clear that it's different. Sum over C D of M C D MDC even C D. That's great, and then 1 over square root D sum over I of I crossed with crossed with I. Nice. Bracket. Again, we can pull things inside of the same sum here, and we get this is equal to 1 over root D of the following sum over I C D M D C I tensor crossed with, my cross is never in the middle of the circle, and now this will be C D I, and it should just be like that, yeah, which ends us here with the same thing as before. We end up with this being Kronecker delta, which forces D to be equal to I, and so we have, this is 1 over root D I C M I C yep, I tensor crossed with C tensor times C. And we can just swap over dummy indices because they're dummy indices, stupid indices. Anyway, this just ends up being 1 over root D sum over AI MAI A tensor cross I. Nice. And that's identical to that. So I actually hate the box. I prefer doing QED, but LaTeX doesn't have, when you do \QED, it gives you the box, and I don't like it. Doesn't matter. So this is our first proof. Just to recap as to what on earth this means. It tells us that for any linear operator M, which maps the FD Hilb or AKA the finite dimensional Hilbert space to itself. Sliding that across the cup transposes it. So now they never tire with the funny names in category theory. What's the quote? A monad is just a monoid of a category of endofunctors or something. I've forgotten it. Wait, let me check what it is. It has just slipped my brain. Like, oh, and I can't even because it's just not working, is it? There we go. What is it? Yeah, a monad is just a monoid in a category of endofunctors. Like, what are these names? I got to the end of those notes and it was two category, and then I remembered that the other word for two category is a monoid or monoidoid. I'll never get over that. Right, let's move on. So now what's a kind of important thing we do is something called the zigzag identity, and I think there's some triviality behind where that's names come from. So it's kind of a topological thing, which is really vital for this, is that if you take a wire and you were to bend it into an S shape, that is topologically identical to a straight wire. And what we do is we prove this using normalizations. But first, let's be clear and have a lemma. So lemma 2 states that, goodness me, this is our cap. Let's see. Oh, brain just broke down for a second. Our wave function is equal to 1 over d over c. Nice. Again, we have more dummy indices here. Well, that's all right. This identity ties everything together because it involves our cup and our cap, which is useful. Also, this is a slightly shorter proof, which I value greatly, because this was not that long to think about, but lots of time to write out. Anyway, getting on with it, we're going to look at the left-hand side first. And we will have some arbitrary state. And we're going to let that equal to the sum over k. Ugh. This. And now we just need to sub in definitions of cup and cap with this, and I think this is an inductive proof even. No, it's not. It's just a proof. So, looking at the LHS here, we get this is equal to 1 over root d times the sum over j of j a cross j b cross ic, and then our second definition, which from here will include, over k of blah, blah, a cross with our thingamajiggy cap, even, that's cup, sorry. No, it isn't. Yes, it is. No, it isn't. Oh, no, it's cup. Goodness me. What is going on? Who knows? Times the sum over I of I, B, tensor product, I, C. Nice. Excusing my terrible handwriting. We can simplify this to be 1 over D because it's going to expand. And then again, we're just going to be lazy and pull everything into 1. K, I, J. Wonderful ordering. I love that. Phi K. Did I remember to write that? I may have forgotten. No, I didn't. Sorry. I'm not happy with this. This handwriting is not acceptable. Simply. Oh. Okay. That's alright. You're allowed to not be having a nice day. No need to take it out on me though. Okay. And now this is going to be in a bracket, and then we're going to bracket J and K. So that's our inner product. A, then another one, and it's the inner product of J and I. B times tensor product did with I, C. I think I've forgotten to close a bracket here. Oh, it was the cool. And now we have a load of Kronecker deltas. So 1 over D, K, I, J. And Kronecker deltas are our best friend in categorical quantum dynamics because they just let us equate variables. Delta JK times delta, it's not really a times, JI, ket I over C. And summing over J forces J equals K, and J equals I actually, so K is equal to I in Ordnung. 1 over D over I of phi I. Oh my goodness, doesn't that look like something? Now, referring back to our definition of phi, of ket phi, A being some arbitrary state, this just simplifies to 1 over D phi C, which is our lemma. Yay! And whilst these are possibly the worst proofs I've ever written, I hope this might make some semblance of sense to somebody in the universe. Now we can actually do something that might be useful to someone. We're going to keep going. And we're going to do an Alice and Bob, because these are computer science notes, of course. We're going to construct a full physical protocol using only the 2 categorical lemmas that we've shown. So Alice has a state, right? As you do. As is a state phi A, which she wishes to teleport, don't we all? Now, Alice and Bob, I'm not going to write things down, I'm just going to speak it. Alice and Bob share the Bell state cap of BC. Cap. I'm still getting to grips with this. No, cup over BC. And so their initial states is A, with the tensor cross of that BC. Now, because Alice is just so incredible, Alice performs a joint measurement on systems A and B in the Bell basis. And the 4 basis states are generated by applying Pauli matrices on sigma over M being in I, X, Y, Z, which I will write down momentarily. So we have sigma M is a member of I, X, Y, Z, and then that's applied to the second qubit of the standard Bell state. So big phi M A B is equal to I A cross sigma M B cup AB. And the measurement projector or cap is the adjoint. And since Pauli's are Hermitian, aka the brain fart sigma transpose M is equal to sigma M. It holds that AB equals to cap AB I A cross sigma M B. That M's not really very near the sigma. Let's write that down. There we go. Now let's apply our measurement. So what we're going to do is apply the measurement to Alice's initial state, which is going to become here Bob, and it's measured is equal to phi M A B I C phi A cross eta BC. And we can further expand so that it holds then that's IA tensor Pauli B tensor cross IC. Am I going to run out of space? I fear so. Tensor cross IC, and then that again. BC. Wonderful. And we can regroup our operators here to act on the cap. So this then becomes here AB cross IC, and then A tensor cross Pauli with IC times BC. Wonderful. Now things start to become simpler because we can use our lemmas. Applying our sliding lemma, or lemma 1, from before onto the system BC, we will slide our Pauli across the cup, which will transpose it So this is going to lead to this AB cross IC. Sorry, this is requiring some amount of concentration from me, to the extent that I'm struggling to read out everything. Yep, BC. And I think we should just be able to pull it out because it acts entirely on C. So IA cross IB cross transpose on C. We're gonna put it in more brackets. B cross C. BC. Okay. And now we have something that looks useful. Because look at the term inside the brackets. That's exactly our zigzag identity from before. And we know that this evaluates exactly to be a half ket phi over C. So this simplifies further. These guys go away, and we get that this is simply a half sigma m transpose phi C, which is wonderful. Why is it wonderful? We've proven that the state collapses once it is measured. Ta-da! So what do we have going on here? We've got a factor of a half. That indicates that our probability amplitude squared is a half squared, which is a quarter. So all four Bell measurement outcomes are equally likely. Notice how we did actually have four Bell measurement outcomes. And they're all equally likely, which is good. And we probably ought to look at contextualize this a bit more. So to complete the teleportation, Alice sends Bob her classical measurement result, which is M. Bob applies a unitary corrections, U, such that U sigma M transpose is equal to 1. So he applies the inverse of the transpose. And since Pauli is a unitary and Hermitian, the correction just ends up being UM. So let's actually apply that, or U star M even. Sigma star M. Let's apply that and see what happens. So with correction, half. I forgot my state inside is equal to half I C, which is just proportional to, keep doing it, which is just proportional to our state. So our state is perfectly recovered, which is the most important thing here, because it shows that the topology of space-time under these lemmas has still acted as a quantum channel, and information has correctly been transferred between the classical measurement and the actual state. Oh, that was certainly a heavy one. I hope that that was understandable. Um, this is quite hard to follow, even for me, as if I'm some kind of mega genius. Um, it was quite hard to follow for me, and I'm the one who's making the video, so I can't imagine how terrible it must have been to watch. But hope it was somewhat interesting. Um, I hope you think it's cool that we can understand this kind of measurement theory, quantum measurement theory, using the basis of category theory. I hope it's interesting that category theory has a use, for goodness sake. I think that's kind of funny. But anyway, I hope that was a good video, and I will see you next week for something new, probably. Oh wait, I forgot to box it. I'll box this because this looks cool. Let's take this down. Yeah. And with that, thank you very much, and I will see you next week. Goodbye.